Okay, so now we are going to move on to Chapter 8. And the way that I've decided actually, I finalized my decision, I should say, into how I'm going to um, section these is I will be putting this up during lab time, so I'll be putting this up around 1 o'clock, as kind of as I stated before, and then on Thursday I'll put in another one up at 1, and then we're having the discussion at 3, which will be talking about that. And then we'll also still have our quiz, which will be online, but it'll be a timed online quiz through Canvas. And so the quiz this Thursday will be going over um, maybe like one thing from last week, more so like maybe one electron configuration. And then this week, it will be mainly on the types of bonds, like this lecture today, just so you know, for the quiz this week. Okay, so let's go ahead and get into the lecture. So, the types of bonds. How can we classify the types of bonding of different compounds? Chemical bonds equal a force that holds atoms together in a molecular compound. So you have ionic bonds and covalent bonds. So we've talked about when you have ions, right? And what are ions? They're a charged atom of some sort, right? So it's a charged particle. So you have anions and cations. So when you have when we were talking about, for instance, the different type of bonds in terms of naming, right? We knew that we had ionic bonds and we knew we had covalent bonds. And ionic bonds were between what kind of ions? They're between an anion and a cation, right? It's between all of the ions. So the two types of ions that we have, that makes up the ionic bonds, all ions. And then you have the covalents, right? Covalent bonds. And what are those? Those are those nonmetals, which are also known as anions. Correct? Right? Yes. So we have our ionic bonds, which are, plus charge and minus charge bonding together. And then you have your covalent bond, which is going to be two negative bonds that are going to be sharing a bond together. Okay? And so we're going to go ahead and talk about each one of those and how those differ and so on and so forth. It would really be a great idea for you guys to pull up your PowerPoints while I go through this and take notes on the PowerPoints, especially if you may not be able to sometimes see certain of the words or something like on the screen, then you at least have it at home in front of you. Okay. So, now, ionic bonds. So ionic bonds is a bond created by electrostatic attraction between oppositely charged ions. So positive electron transfer, or an electron transfer will happen between the positive and negative charges. So opposite charges attract. So as they say, right, opposites attract. So when you have a positive and negative, they attract. Just like in our ionic bonds, what do we have? An anion and a cation, and those are going to be attracted to each other. So electrons transferred between cations, which are metals, and anions, which are nonmetals, is an extremely strong bond. So when you think about like a magnet, so you have like one positive end and one negative end, and so when those come together, it has a very strong connection, right? There's a really strong force that's happening between them because those opposites are just automatically attract, and they're just kind of like a magnet. So they just come together. So it's going to be a really strong bond between this positive and negative charge that's happening. So covalent bonds. So we've discussed covalent bonds in the past, right? In terms of, we know that covalent bonds are dealing with nonmetals, so which are also anions. Yes, anions. So a covalent bond is a bond created by the sharing of electrons between atoms. So sharing the electrons. So unlike the ionic bonds you have to have a positive charge and a negative charge, and those are automatically attracted to each other. So they come together like magnets. So you have like Na and you have Cl. Na is a positive, and Cl has a negative. So they're just like little magnets. They come together and link on. But in a covalent, right, we don't have that connection between the attraction of the different charges, because they're both nonmetals. So how do they create their bonds if there's no automatic force, electric force that's pulling them together? Well, what they do is they share. So instead of having that force, they kind of lightly, it's almost like they're holding hands. They kind of hold hands together. They're not attracted with this strong pull, but they're like kind of lightly like, oh, well, you know what? I can kind of share my electrons with you, and I can share mine with you. And we have kind of this looser bond of sharing. So you can have an equal sharing, which is going to be called nonpolar covalent, or an unequal sharing of electrons, which is polar covalent. So when you think of nonpolar, right, what I like to think of is that when something is nonpolar, it has no pull. So there's nothing that's going to kind of be pulling on either end, right? When you have when you're sharing something, there's no person is going to be pulling the other end. So there's like unequal pulling. It's like a tug of war. In the beginning, there's a flag in the middle, right? Let's see, this is my little tug of war. Let's see here. This is my little flag, and I have all these people right at the end holding on to this rope, and this is even right now. Excuse my people. So this is even, right? Let's say this is right in the center. So there's an equal sharing of electrons. So let's say if this was an electron, right? Let's say if this was N2, right? So you have N on this side, and it's bonded to the N on this side, and they're equal because they're both N's. They're both nitrogens, right? So if you had N's on both sides, then it's just an equal sharing. Like this one isn't going to be stronger than this one, right? They're an equal amount. So there's no pool. But if there's an unequal, which is a polar covalent bond, there's going to be an unequal sharing of electrons. So there's going to be one that's going to be pulling the other in terms of electronegativity. So one's going to have like a stronger pull and being able to pull electrons towards it. So if it has a stronger electronegativity, it means it's almost like it's a stronger magnet for electrons. So it's able to hold on and reach even further for electrons. So it might pull one side towards it a little bit more. So you might have an unequal sharing, which means there's a pull. So the way I like to remember polar covalent and nonpolar covalent is there's no pull for nonpolar. So there's going to be, which means it's an equal sharing. And for polar, there's going to be a pull on one side. So which means there's going to be an unequal sharing. Because if one person is pulling harder than the other, then that's going to be an unequal, right? So I hope you got my little example. Okay, so just remember that polar covalent is unequal sharing of electrons, and nonpolar covalent is an equal sharing of electrons. And that a covalent bond is a weaker bond than the ionic bond, right? So like remember I said the ionic bond, so it has this magnetic force, electric force connection. These charges automatically come together like magnets and can't help it, really strong. And then the covalent bonds just kind of nicely share electrons. There might be one pulling, so it can be an unequal sharing, or it might equally share. And the unequal sharing is polar because there's a pull. So there's pulling, so there's polar. And then there's no pulling, so it's equal. So that's an equal sharing. There's no pulling. Okay. Let's keep going. Okay, so electronegativity. The ability of an atom to attract bonding electrons. So between the atoms in a covalent bond, a difference in the electronegativity. This is where you basically have to look at when you're looking at being able to decipher if something has a pull or no pull, you have to do so using electronegativity. So, and electronegativity is how much attraction does this have for bonding electrons. So that pull that I was talking about, that is the electronegativity, which is the ability of an atom to attract bonding electrons. So polar bonds, which are, there's going to be a difference in electronegativity, right? Because polar, there's going to be a pull. So there's going to be an unequal sharing. So those typically to be shorter and stronger bonds, which makes sense. There's something pulling. It's going to be a little bit stronger. It's going to be tighter. So it's going to be a stronger bond. It's going to be shorter because it's so tight. And then there's no difference in electronegativity. So the electronegativity is the same. Then you're going to have that's the nonpolar covalent bond. And so those are typically kind of longer and weaker. So you kind of just see them as like, oh, well, they're just kind of floating together, just like a little bit longer and just weak. Versus the polar ones are going to be a little shorter, tighter, and stronger. So if they're tighter, right, it's going to make kind of the shorter bond if it's tight. And if it's looser, it's kind of going to be a longer bond, right? That kind of makes sense. Okay, so we last time discussed different trends that the periodic table can have. There we go. That's better. So this is one, it would probably be a good idea for you to pull up the PowerPoint if you can, like on your phone or on something else, so that you can actually see this picture. So I'm trying to make this come up, but it's, I don't know, something's wrong. Okay, so when we talked about the different trends of the periodic table, right, we talked about atomic radius, which is the distance from the nucleus and to the circumference, or the distance from the furthest distance out from the radius, from the nucleus, right? So if you look at the circumference, if you take that in half, that's going to be the radius. And so remember that depending on the quantum level of the actual atom, like where it's actually placed, that will kind of tell you how large the radius is going to be, right? So if you have more quantum levels, it's going to be larger. So you're going to have a larger radius. And so then we did a periodic trend with that, as well as we did ionization. So ionization, right, is how much energy is needed to take away an electron from something. So when you're ionizing, you're taking an electron away, right? So how easy is it for that energy to be separated? And the electronegativity is the opposite. How strong is it going to be pulling it towards itself? So ionization is the separation. Electronegativity is like when it's coming together. So the trend for how tightly held they're going to be is this. And so, like I said, I like to follow the same direction, right? Because it just makes me just makes more sense to me. So I think to myself, well, how do you write an E? I know that sounds silly, right? But how do you write a capital E? So you write an E like you start here, go left, right? So the trends for the electronegativity is that it decreases in this direction and it decreases in this direction. Okay, and so I always like to remember it this way because electronegativity, right, it starts with an E, so it decreases. When you write that E, just think to yourself, decrease, decrease. decrease, so decrease, 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 decrease for electronegativity. So when we're talking about the polar and nonpolar covalent bonds, right? So remember that when we're talking about polar and nonpolar, that's dealing with the covalent bonds because we're talking about them sharing. The ionic bonds aren't sharing electrons, right? They're creating this magnetic force or attraction. So that's why you talk about the pooling and non-pooling with the covalent bonds. So using this trend, you're able to see what bonds are going to be polar and which ones are going to be nonpolar. So which ones are going to have some sort of pool and which ones are not going to have some sort of pool, right? So based off of this, like when you look at this periodic table, if we said that it decreases this way and this way, right? So decreases like that, right? So then you should know that cesium is going to be the smallest, right? And even when you look at the values on here, right, you can tell, well, really, it's not. It's the FR, which I actually found FY. So francium. We never use that. So I wasn't sure what that was. Well, it's not common. But so francium, so that is the smallest, right? So decrease. Decrease. So this is going to be the smallest, and then fluorine is like the largest, right? And you can tell that based just even off of the values. And so as it decreases this way, so if you had a bond between carbon and oxygen, right? So we have a bond between carbon and oxygen. Looking at this trend, which of the two is going to have a higher electronegativity? It's going to be stronger in electronegativity. The oxygen. So the one that is the closest to this end, right? Because we decrease as we go over, we decrease as we go over, and decrease as we go down. So I can tell that the oxygen, even without these values, right, without these numbers just help you see or what the actual value, their actual electronegativity is, and put in this periodic table. In this way, you're able to kind of see how the trend actually, like with values, how to follow it. So, right. So oxygen, right, is here is more, I guess, to the right of the periodic table than the carbon. So therefore, oxygen is going to have a stronger electronegativity than the carbon. So the oxygen is going to be pulling more, right? Because if it has a stronger electronegativity, that means it's going to pull more. So the oxygen, and the way that we actually denote the one that has more of an electronegativity is by this sign here. It's called delta negative. And then the one that is going to be not as negative, right? The one that doesn't have the pull, that's not as negative as the other atom, it's going to be the delta positive. So this one's delta negative because it has a stronger pull. It's pulling the electrons. So this one's kind of leaning towards this, right? The pull is in this direction because this is going to be higher than this. And the last way that we actually finished writing or how to indicate something that has like some sort of, it's a polar covalent bond, is drawing the arrow of directionality. So if we're saying that our oxygen is more electronegative than our carbon, right, then the oxygen is literally like pulling the carbon towards it with all its negativity, basically. So it's like all this negativity, that the oxygen is just like, I need your negativity. I'm so negative. I'm going to pull you and make you a little bit more negative. So we're going to actually draw an arrow that represents that pull as well, and the directionality, as I said, of the electronegativity. So we're going to draw our arrow, and what direction would you think? Towards the side that's being pulled, right? Or towards the side that's pulling. So our arrow is going to go towards the negative, because that's the side that's pulling. And then on the positive end, that's where we put a little perpendicular mark all the way through. And I like to think that this side is the positive side. And so the positive side goes with the delta positive, right? So we're going to have the arrow going towards the side that's pulling. So when I'm pulling this side, that's the direction of the pull is towards me, right? The direction of the pull is towards more negative. So the little cross is going to go on the side that matches up with the more positive side. So it kind of looks like a little plus to me, right? Okay, so hopefully this is all making sense. All right. So obviously the best way to learn is to do examples. Okay. So, which of the following molecules contain polar bonds? If a polar bond, which atom has the partial negative charge? Okay, so let's, sorry about that. So let's go back to this beginning little chart. So when we talk about the bonds, right, type of bonds, there's two types of bonds. There's a covalent bond or an ionic bond, right? And the ionic bond involves what? Positive and negative charges, which is an anion and cation, or metal and nonmetal. And then you have covalent, which is going to involve two nonmetals. So this ionic is going to be an electrostatic connection between the positive and negative charges, and the covalent bonds is going to be through sharing. So with the sharing, there can be two kinds of sharing, right? You can have your polar covalent, and remember the polar is the one that's going to have the pool. So the pool is going to have more pull than others than one of the other atoms. One is going to have a stronger pull. And the nonpolar is like no pulling, so it's not going to be pulling as much, or there's going to be an equal sharing. There's going to be no pulling. Okay, so if you were to, once again, these are just different ways to kind of look at all of this stuff. So if there is no transfer of electrons and there's an increasing transfer of electrons, and then that goes to a complete transfer of electrons. It's kind of like, that's ionic, right? Is when there's no transfer, and then there's like maybe a complete transfer. And then the no sharing of electrons, that's how this is where they start, right? You're not transferring anything, you're not sharing anything. But then as you're increasing your transfer, you're going to a complete transfer. And as you're increasing your sharing, you're going to an equal sharing or an unequal sharing, right? But some sort of sharing. Okay, so let's go ahead and do these problems. Okay. All right, so okay, so the first problem that we have is which of the following molecules contain polar bonds? If a bond is polar, which atom has the partial negative charge? Okay, so with and then the last part is which bond is the most polar? In formulas of compounds, the first element is the central atom. So we're actually going to today also learn, we're learning about bonds and the different types of bonds, so then we can actually learn how to kind of write out the bonding for all of these chemical formulas that we've been putting together. So we've been writing them out in their formula names, right, as well as like their complete names and their formula names. But there's also an actual atomic structure, right, in terms of how these bonds are connected with lines and things like that. So with these bonds, we're going to learn about the bonds, and then we're going to go into how are they all put together. So in order to understand the polar covalent and nonpolar covalent, we have to kind of set up a couple of structures so that you can see how the concept works. Okay. So in the first example, so anytime you're doing these, we're going to be writing these formulas out in structures, right? This hint, right, in formula compounds, the first element is always going to be the central one. So for when you're drawing these, right, your first one is going to be the center. So for sulfur oxide, you're going to have the sulfur in the center, right? And then you just would have two oxygens. And let's just say that this is, it could be bent. I'm not sure yet based off the number of electrons. We'll learn about all of that later. But right now, we know it has two things bonded to it. And what are they? Oxygens. So you would have something in here. And so the next one is N2. So that's saying that you have N connected with N. And then you have pH. So you're going to have the P in the center. And then you're going to have H, 3 H's surrounding it, right? Because the P is first, so the P is in the center. And then the D, which out of the carbon and the chlorine is going to be first? The carbon. So you're going to have carbon in the center, and then 4 chlorines surrounding it. Okay? So these are just some basic structures that are not fully done in terms of their full Lewis structures, but it's just to help you guys understand how to see or differentiate between the polar and nonpolar covalent molecules. Okay. So now, right, if we want to figure out the following molecules contain which ones have polar bonds, and then if they're polar, which one has a partial negative charge, right, and which atom of this compound is a partial negative charge, and which of the bonds is the most polar, right? Which one is going to have the most pull between the bonds? Okay. So we just went over how to differentiate, right, between a bond. So every time you're doing something or trying to figure out if something's polar or nonpolar, you're just going to be looking at one bond at a time. So you would just look at this bond first, O and this S, right? Because this could also be something else. So it may not necessarily always be SO2, right? It could be SO something. I don't know. Just saying, it may not be always the same thing. So you want to look at each individual bond. So that's one bond. So if we pull this out and we look at this here, now when you go back to your periodic table and you want to look at the electronegativity, right? So let's look at our periodic table. And let's see where oxygen is. So we found oxygen, right? Now where is sulfur? Oh, it's under here. So when we remember how I told you when you're writing your E, right, it decreases, 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 decreases. So if it's decreasing in this direction, right, and the oxygen is above the sulfur, right, so the oxygen is going to have a stronger electronegativity than the sulfur. So the oxygen will get, so what would you think the charge would be, the partial charge of oxygen would be? It's going to be the one that's more electronegative. So it's going to get the partial negative charge, right? Because it's more electronegative. So you put your partial negative charge with the oxygen. And then, because this is more electronegative, the opposite gets the partial positive. So this gets the partial positive, right? And then in which direction we draw our arrow? Towards the more electronegative, right? Because the electronegative one is the one that's pulling. So if it's pulling towards. And then the plus goes on the side. And you don't put a circle around it. I just wanted to circle the plus for you just so you can see that it's a plus. So hopefully you can see this. Okay, so when we look at this, right, and now let's go ahead and put this back into this state here, right? So we know that we just broke down the oxygen and sulfur, right? And so we just said that this is a partial negative here and a partial positive. So since this is the same thing on both sides, we know this is going to have the same electronegativity in terms of the pull, right? Because oxygen is going to be more electronegative than sulfur. So I'm still going to put the electronegative, the partial negative on this side. So there is a polar bond here, right? Because there is one that's more electronegative than the other. So there is going to be pull. But because it's the same atom, and on the other side, it's going to have the same exact pull on the opposite side. So this side is pulling at the strength of oxygen, almost, the electronegativity strength of oxygen, and then this side is pulling at the same strength, because it's the same pull, because it's the same atom, right? So it has the same strength, the same oxygen strength. So therefore, these pulls end up canceling out. And it makes it almost equal, right? Because it has the same pulling on each side, so really nobody's pulling because they're equally pulling at the same rate. So therefore, it's almost like these cancel out, these cancel out in terms of being polar, and therefore you have a non-polar molecule. Okay, so this is a non-polar molecule. All right. Okay, so let's do the next one. So the next one is nitrogen and nitrogen. Well, even without looking at the periodic table, they're the same element, right? So since it's the same element, there is not going to be any pull because they're the same thing. You can't pull on yourself, right? You need someone else that has different strength than yourself. Like, I can't pull on my arm, right? I'd have to have someone else actually for me to really pull myself. I'd have to have someone else pull me. So because it's itself, this is also going to be non-polar. Okay. So let's look at the H3 or pH3. So when we look at phosphorus on here, we know it's here, right? And hydrogen is here. But remember, I was telling you sometimes hydrogen really has like properties of here, right? But technically, it's a weird one. But just know with everything for hydrogen, hydrogen is always going to be the less electronegative atom. So no matter what compound that you're looking at, hydrogen will always be the least. It's the least electronegative atom that there is. So if there's anything that's trying to connect with it, it will automatically have a pull, right? So if that being true, hydrogen would then have the partial positive, right? So because when you remember that you want to look at each bond individually. So if this is a bond, if there's a partial positive towards the hydrogen, and then that would make this phosphorus a partial negative charge, right? Because the phosphorus is going to be pulling more because the hydrogen is going to, that never has a pull. So then our arrow is going to be going in this direction. And since all of these bonds are the same, right? It's hydrogen and phosphorus. It's going to have the same pools. So we're going to have this as partial positive, and so our arrow is going to go in this direction, right? And this is also partial positive, and our arrow is going to go in this direction. So now, if you can see, we have our three arrows, right, that are going, our arrow for this bond, H and P is going in that direction, this one's going in that direction, and this one's going in this direction, right, because they're all the same, it's all the same bond, it's just three of the same thing. So this is going to have the same pull as this one. This is pulling in, and this is pulling in, right, so that these are going to equal each other out, right, these cancel each other out. These are canceled out. But there's still a pull left, right? So even though, see, these is equal sharing here, but there's still, because there's one bond that doesn't have something else that can cancel it out, this can be considered still polar. Polar, because there's still some sort of pull, right? It's not a very strong pull because hydrogen is really lightly connected. It's just a really light, like really low in terms of electronegativity, but there still is a pull. So this would be considered polar. Okay, and then we have our last one. Once again, all of these bonds are the same, right? Carbon and chlorine, carbon and chlorine, carbon and chlorine, carbon and chlorine. So when you look at carbon, let's look at that on our periodic table. Wait, carbon and chlorine, right? Okay, so if this is decreasing in electronegativity, right, and so we're decreasing as we go this way. And we had to go over 1, 2, 3, 4, 5. And this went over 2 and went 2 down, but it went over 5 more, right? So this one is less electronegative than this chlorine, right? So the chlorine is going to have the partial positive, and the carbon is going to have the partial negative. Does that make sense? Because here's the carbon, and then the chlorine is here. And if we're decreasing, and this decreasing in this direction and over, as you come down, we only went down 1, 2, right? But when we had to come over to get to chlorine, to get over, we had to go 1, 2, 3, 4, 5 to get to carbon, and 2 to get to chlorine. So therefore, the carbon is more in the periodic table, is going to therefore be less electronegative than the chlorine. So you're going to have your partial negative at the chlorine. Yep, right? And then your partial positive is going to be at the carbon. And so that will be true for all of these bonds. So here you'll have a partial negative here, partial negative, right? Because they're the same bonds. So you have, so in that, I can draw all of my arrows. And remember that your pull goes towards the negative, right? Because your plus goes with the positive. So this is going to go in this direction. They all go out because the positive is in the inside, partial positive. So you're going to have your arrow going out towards the chlorine, arrow going out towards the chlorine, arrow going out towards the chlorine, arrow going out towards the, oh yeah, I already did that. Right, so, and each one of these is going to have the same pull. So basically, the only time, like this last one with the pH 3, this is polar because it had an uneven number of pools. So here we have 4 different pools of the same element. So that's going to kind of equally cancel each other out. So if you actually thought it was like kind of like tug of war, so these are pulling in this opposite direction out, like this, right? So equally. And then these are pulling in the opposite direction like this, pulling out equally. So here, because these cancel out, there's no pool because the pool is equal on this side and it's equal on that side. So therefore, that would make this non-polar. Hopefully all this is making sense. I mean, we'll obviously revisit it, but hopefully it's making sense. All right, let's continue. Okay, so now let's go on to ionic bonding. Okay, so ionic bonding, what is the nature of of the bonding on ionic compounds? Elements, which are mainly main group, right, not transitional elements, either lose or gain electrons to become isoelectronic with a noble gas and reach the octet rule, i.e. have the same electron configuration. So we've talked about this several times when we talked about ionic, like naming ionic compounds, right? And then a second ago we also talked about it with looking at the type of bonds, right? And so when we think about naming, right, we know that each element, all the elements except for the noble gases, are all trying to get to the octet rule, right? They all want to be happy and be satisfied. So therefore, each row of these main groups has a certain number of electrons that they're going to lose or gain so that they can finally be a part of the noble family. So when you're starting over here, right, so this group 1A, that's going to be your alkali metals, or your alkali metals, right, which is like your sodium, your potassium. So those are going to have a what charge? +1, right? And then your second row here is going to have +2, remember? And then this is going over here is going to be a +3. Yes, and then as the same is true on the opposites, and then you have -1, -2, -3. Okay, and then these, the reason it's green with 8, because it doesn't gain or lose any, right? It just has 8. So just remember, like, when we're talking about the ionic compounds, right, and you're combining these things together, like, for instance, when you have sodium and chloride, sodium loses 1 electron, and chlorine what? Gains 1 electron. So when you combine those together, that's actually what's happening, is that the sodium is actually giving its electron to chlorine, and chlorine's like, hey, thank you, finally, I feel so much better. And sodium's like, thank you, I needed to lose like a little extra weight so that I could just be noble. And he's like, yeah, I know, I was so close, I just needed that $1 extra so that I could be noble, and now we can be together and we're both noble, right? Kind of works like that. So that's kind of how the bonding is that when you're losing these electrons or gaining these electrons, spray too much. When you're losing these electrons or gaining these electrons, you're actually kind of giving them to the other, they're actually giving them to the other element. Unlike the covalent, right, they're just sharing them. They're just like, hey, like, we can like share, kind of hold hands, and I'll like share this like with you, and you can kind of share this with me. And so we might have, one of us might be a little bit stronger and have like a stronger arm and kind of pull the other closer. So it might be an equal like pulling, but we can share. And then the ionic bonds are actually giving things away and taking things. So when you look at the example I was talking about, sodium, and you have chlorine, right? Chlorine is actually like taking this, and he's like, oh my gosh, I want to give you, here is my plus. I'm giving you my plus. That's my hand, or a hand, I'm not sure. Yeah. But he's giving this, not plus, he's giving away an electron, right? Because that's what the positive means. And then the chlorine is like, oh my God, thank you, let me take that from you. So he's taking this electron. So, So when we had talked about there's going to be chlorine adds on another electron, right, and sodium gives it away, this is where that all comes into play. Is it's actually giving it to the other atom or taking it away. So let's do some basic examples that you guys should already know how to do, because we've all gone over naming and we're all fantastic at naming. Okay. So, when we look at these namings, how many electrons will usually be gained or lost by each of the following atoms? So this is just literally asking, what are the charges for the following elements in this example? So, what's the charge of bromine? -1, right? So you just write minus. What's the charge of barium? What row is that in? It's in the second column, so it's 2+. What is the charge of potassium? Well, that's in the first alkali metal row, so that has 1 positive charge, right? And then you have aluminum, and that has a +3 charge. And then oxygen is going to be a 2- charge. It's in that second row to the right. And neon is a noble gas. Therefore, no charge. Tricky, tricky, tricky. Okay. Oh, shoot. All right, so let's continue. Okay, so how do we actually write out these structures? So we, just like I was showing you how there's bonds that are connecting things, and you have covalent bonds and ionic bonds. Well, how do you actually write this out on paper? Like, how is that written so that you can see these bonds, right? So that's through this concept called the Lewis dot structure. So we're actually going to use dots in order to diagram the electrons in the outermost shell, which is the valence electrons. So dots are placed around the element's symbol, which represent the valence electron. Pair electrons as needed. So when you look at this lithium, right? So lithium is the the element, and the outermost shell. So remember how you have to figure out what the outermost shell is. So in order to figure the outermost shell, what is the highest number that's in this electron configuration? 2, right? So that is going to be the valence shell, the outermost shell. And then you have to add up all the electrons that are within the orbitals. Here we only have S, and there's only 1. So we have 1 electron in our valence shell. So they wrote Li with the dot, because the dot represents the 1 electron. So when we look at the next one, beryllium, here, what is the number of the outermost shell? 2. And we once again only still have 1 subshell, but here we have 2 electrons in those subshells, so the valence electrons that are available are 2. And here we wrote 2 dots next to the beryllium, right? Because there's 2 electrons, 2 valence electrons, and so on and so forth. So let's go into boron, right? So here we look at what is the highest number. Well, we see 2. But here we have 2s2 and 2p1, right? So we have to add up all of the electrons that are in these suborbitals. So because we have 2s2 and we have 2p1, we have 2 plus 1 is 3. So we have 3 valence electrons. And so that's why we have 3 dots that are written around these valence electrons. And that's just kind of the rest of this chart is just giving you more examples of those things. So if we looked at this last neon, right? So, how many electrons can be in a valence shell? 8, right? Because we have to, the maximum number that they can have, as we learned earlier, is 8. All of them want 8. They can't have more than 8 because they just want to be noble, right? So when we look at neon, we see, okay, well, what is the valence shell? Well, quantum level 2, right? The quantum level 2 is the valence shell. How many suborbitals are there? There's 2. There's S and P, which are both full. So we have 2s, or S2, and then P6. So we have 2 plus 6, and that equals 8. So that's why there's 8 dots that are around neon. Right? It's pretty cool. Pretty cool, I think. Okay, so let's keep going. All right, so best way to learn, as I always say, is through examples. All right, let's make sure, see if I can get all of this in here. Okay. All right. So, Lewis structure for selenium. So let's go and make sure that we know what these are and where they are, right? So let's see. If you guys run, like I said on the last, I think, video, I said that we all have a periodic table at the end of our lab notebook, right? So this has the periodic table, and it also has the list of all the names of all of the elements with their symbols as well, just an FYI. So we are looking for selenium, which is Se. And so Se, let's see, where is Se? So Se is going to be 34. Okay. So if we were to do, so Se, 34. Yeah. So Se, let's say Se, 34 electrons. All right, let's start with that. So the first thing that you want to do when we're having to write out these Lewis dot structures is you have to say to yourself, well, what am I doing? I'm trying to figure out how many valence electrons there are so that I can put the correct number of dots, right, around this structure. Well, how do I figure out how many valence electrons there are? Well, I have to figure out what the electron configuration is of this element, right? So if we have Se34, so remember how to do the electron configuration. You want to say, so cesium is here, right? And so if we have 1s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 2, 3, 4. 4p4. Okay, so sorry if you couldn't see that. So this is 1s2, right? 2s2, 2p6. 3s2, 3p6. 4s2, 3d10, and 4p1, 2, 3, 4. 4p4. Okay, so I'll just go ahead and write that out. So we just said it would be 1s2, 2s2, 3. 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. Okay, So when you're looking at this electron configuration, right? So we have this electron configuration here. So what is the highest quantum level, right? Which means what is the biggest number? What is the biggest quantum number? So we have 1, 2, 3, and 4. Well, 4 is going to be the biggest quantum number. So we're going to be looking at here and here, right? So even though this 3D10 is in between the 4s2 and the 4p4, it's still not the biggest quantum shell, right? Because it's the principal quantum level is the number, so the biggest number. So then you want to add up the number of electrons that are in that outermost shell, in that largest quantum level. So you have 4 plus 2 equals 6. So there's 6 valence electrons in cesium, right? Okay. Okay. Also, another trick, right, to figure this out instead of having to always write out the full electron configuration, it's always good to write out the electron configuration, especially, obviously, if I ask. But if you just need to actually write out the Lewis dot structure, an easy way to not have to go through figuring out all of the electron configuration is to actually look at the numbers on the periodic table. So we just found cesium, right? And you see cesium here. And this rule that I'm going to teach you only is dealing with the main group. So 1, 2, 3, 4, 5, 6, 7, right? Okay, so just the main groups. So cesium is here. And what did we just say? We just said that there's 6 valence electrons, right? That we just found out. Well, so since cesium's here, there's 6 valence electrons, we said. And when you look here, I know this says 16, but you just want to think that that you're just going to use the 6, right? So you see there's 6 valence electrons in cesium. So these numbers are then going to apply to how many valence electrons are in each of these elements that are in these rows. So carbon is going to have 4 valence electrons. So is silicon and all the rest of these in this column. Boron is going to have 3. You see how it says 13? So it's going to have 3 valence electrons. And this whole row is going to have 3 valence electrons. This whole row is going to have 5 valence electrons. This one's going to have 6. This one's going to have 7. This one's going to have 8. Right? Do you see that? This one is going to have 1 valence electron. Remember Li? It had 1. And then Be, it had 2, right? So you used to use these numbers. So these numbers here, and remember to take off the 1s in the beginning of these. And those actually are how many valence electrons. So that's actually pretty cool. So it's just another pretty cool way to be able to figure out drawing the Lewis dot structures without always having to write out the the full electron configuration. Okay, so let's erase some of this so that I can actually write the dot structure here. Okay, so we just said cesium, right, has 6 valence electrons, right? Okay, so now let's draw this dot structure. So remember that we're just drawing the dots, right? So all you have to do is now put SE and just write how many electrons, draw the number of dots of electrons around the element. So I just did 1, 2, 3, 4, 5, 6. Okay? And generally you do write them all around once and then come back. It's almost like following the Hund's rule, how you're having to fill up each spot and then come back and fill up the other spots, right? So you're not gonna write them like this, okay? Because you see, like, I'm not covering the entire thing. So you want to, because this is really to do what? To show the number of bonds. So each little electron can create a bond. So they want to be as far away as possible on this. That's kind of the way you want to think about it. So you want to have these dots like here, so that can create a bond. This can create a bond, right? Before you have 2 bonds or however many bonds on this side, you want to be able to each side have you create a bond and then add the other electrons. But yeah, so the final answer for this then would be cesium. I have 1, 2, 3, 4, 5, 6. Okay? And then for the next one, which is rubidium, so rubidium, we did this earlier. Okay, here you are. So here is rubidium, right? So I just am going to go ahead and write out the electron configuration so you guys can just keep getting the hang of how to do so, because like I said, and more than likely I will, when asking you to write out the Lewis dot structures, I will ask you to also write out the electron configuration for these things, okay? So, if RB is here, right? So let's go ahead and write all of that out. So RB, so if we just go ahead and go through all these rows, right? So let's go through all these rows. So you have 1s2, right? 2s2, 2p, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, because rubidium, right, is in the first S column. So we can just write that out for RB. Is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Nope. Yes. Yes. 3p, 4s. Yes. Okay, so, right, in order to do these Lewis dot structures, you have to find how many valence electrons there are. Okay, and how do you figure out how many valence electrons there are? Well, you want to see which one has the highest number, right? Quantum number. So 5 is the highest quantum number. So how many electrons are in 5? There's 1, right? So RB has 1 valence electron. So now if you did it the quick way, right, you could come to this, your periodic table. Now what column is rubidium in? The first column. So it has 1 valence electron. So cool. Makes life so much easier, right? This is how I feel. So if it has 1 valence electron, then how would I write this? RB with a dot. And it doesn't matter where you start your dot. You just want to, if you have several dots, you just want to start, you want to have them in 4 spots around the element. But it doesn't matter at what point you start. You start at the top, you start at the bottom, as long as it's on one of the sides. Okay? All right.